Welcome back to another OpenGL tutorial, and actually I'm not just going to use OpenGL, but I'm going to also use GLSL too, so OpenGL shading language. The reason is I want to merge the OpenGL and the GLSL series into one series, because the thing is that in the OpenGL series I kind of use old OpenGL, kind of use new OpenGL, and I want to merge these together and make only new OpenGL, because I use fixed spline and I'm also using immediate mode and the building matrices, and all of these are actually not available after OpenGL 3.1. So it will be a good thing. Actually, this is my goal for now, to change all of these to just the new OpenGL, and to do that I also need GLSL. Okay, but this tutorial is not specifically about this change, but this is about how to make a new kind of model loader. Actually, we are not making a model loader, we are using a model loader called OpenAssetLibrary or Assimp. And a special thanks to go to Dimitri, who suggested this library to me. I have never heard of this library before, but I just tried it and this is awesome library. So right here I just did a Google search on Assimp, and the first link should be the site where you should go if you want to install this, or just check this out what it can do. So it is a library made with C++, and it supports a huge amount of model format, and the good thing is that all of these model formats will have the same interface. So right here, if I just click on this 3D model format, it shows how many model formats does it support. It supports directly the .blend file, so if you just save it out from Blender. It also supports, as you can see, almost everything. I don't even know if there is a model format which I can think of which is not supported in here. As you can see, all of these model formats are supported. It also supports animation, more precisely just load in the animation, don't do the bone animation for you, but with a little work and with the built-in types like water neon and matrices, we can easily make working bone, so skeletal animation with it. So it's a pretty good library, and not matter what format are you using OBJ, you're using .blend format, or you're using .md2 format, so whatever format you are using, you will have the same interface in the program, so you will pretty much load in the same way and you are pretty much using it in the same way. So let's see how to download. So go to the download page, obviously, go to the newest version, which is Assimp 3.0 currently, but if there is a newer version, then download that. Alright, and just click here to actually just search for a version which you would like to download. For Linux, this is the version you want to download, this full. So Assimp 3.0.1270 -full.zip. This is for Linux. I tried this, I installed this. I'm not quite experienced with this other format. Probably for Windows you want to download one of the exe. I will try it at the end of this tutorial and cut this somewhere right here to have to install that on Windows. Anyway, if you have downloaded it, the next thing is to extract it, obviously, and I already did that right here, Assimp, and extracted the folder, so here it is. So now if I just go into this, we can make a folder. Actually, let me get a terminal, and right here the terminal, and I had another terminal. Anyway, so let's go to the folder, Assimp, and let's make a folder. So I'm going to call this build 3 because build 1 is my primary build, build 2 is the tutorial which doesn't quite work out. So build 3, and then just go into the build 3 folder and we can make this. So on Linux you can use the cmake. This is a tool which is going to make a make file, so you can make with make. Alright, so cmake .. which .. is representing the previous folder, so we are making we are building the Assimp. So just click on this. This should quickly try and go over everything. And by the way, the last I had one problem, that this boost library was not installed. If you get a similar stuff, then just do sudo apt-get install lib boost lib. Right, and just install the libboost/-dev, and that should solve your problem. Anyway, you have cmaked it. The next step is to make it. So just write make, and this could take a while it do that. So just wait for it and don't interrupt it like I do. And then after you have finished that, let's just place the necessary files to where your compiler search for it. So sudo make install. And if you press and if you do this, this will copy the necessary lib and include file under your /usr/local/something libs and include. By the way, I'm not sure if you need to put your files from /usr/local/include to /usr/include, but I usually do that, so I usually just making sudo cp /usr/local/lib/lib assimp right to /usr/lib. Just in case if my compiler search for it. I don't remember if it is necessarily needed or only I do it, but if it doesn't work out, then just copy your files to there and it should work. Okay, now that the installation is finished, now we are ready to make some modification to the actual program, because this should be a programming tutorial. So what is needed to be done is actually I opened up the program from the first GLSL tutorial, because as I mentioned, I'm going to use GLSL and I'm not about to type it again. So I'm not about to type it again, this load shader stuff, because it's relatively long. So I just load it up, and of course you can use whatever version of GLSL tutorial you are currently in. Even if you want, you can use still the fixed people in, so without GLSL I will tell where the difference will be, because loading the file will not make any difference later on when we actually using the vertex buffer objects. Then you have to use this for loop similar to what I have used in the original OBJ loader tutorial. I have already also created a few files which are the load scene file. I created two. This will load the scene and also store the meshes. There could be several mesh in a scene. So there could be one ball and another ball and a cube, so on. So there could be several meshes in a scene. This scene will hold a vector of meshes. Right. What is the next? I have this mesh data.h. This will be a simple header file to store actually two simple structure which will be needed. So let's start with this. So I use the inclusion guard as always, because at least two of these files will include this, the mesh and the load scene function. Although if I don't include this into the load scene function, only in the mesh, then I don't need it. But anyway, just let's make an inclusion guard. So mesh data_age, then define mesh data_age, and this. So the two simple structures is actually, the first one is storing the data for a simple vertex. Simple vertex we need data like the position, the normal vector, and I'm also going to store a few additional data like the tangent for making normal mapping working more better than the original. I'm also going to use the colors and the UV coordinates. So I have several stuff which I'm going to store for a single vertex. I'm going to place it in the simple structure right here. So if I need to change, I want to store, I don't know, some additional data like a second color or a second texture coordinate, or store some simple data like is it a light source, which we will see later on why would be useful. So I'm going to just make it struct and I will call this vertex data. And before I forget, I also need to include the vector 3D. So include, and I include the vector 3D.h. If you don't remember, this is the vector, it is a three-dimensional vector, obviously. Right, so what we will need is a position. So vector 3D position. I also going to store the normal vector for each of the vertices, so we can do smooth normals. Vector 3D and normal. I'm also going to store the tangent space. So vector 3D tangent. This, by the way, if we don't have a tangent space, we just leave this out. We don't even care in the fragment or the vertex shader about this. So we send this uniform, but we don't use it. So pretty much we avoid it. I'm also going to store the color for each vertex. Color. We don't necessarily have color. Most of the time we have position and normal. We don't necessarily have these two. And the last thing is the UV coordinate. So this is not a vector 3 because we have just two components, a U and a V. You might want to optimize this out, so make another structure which don't have tangent and don't have color. But for now I just leave it right here because it's not that big. In data size, yeah, they are, let me count, 24 bytes per vertex. I don't feel like optimizing this out, but if you want, you can make something like delete these and, just store the data which you will actually use. We probably also use the tangent and the color, so I just include it into right here. The next thing is I am going to store textures, and the textures, as you probably remember, is just an unsigned integer, but sometimes later on we will want to use other kind of textures, which are, I don't know, normal maps and bump maps, which are probably the same. Anyway, so we want to use different type of textures, so I'm just going to make a simple structure with 2 elements. So let's make the structure, and I call it texture data. The texture data is containing the ID, and also is containing a type. So later on we can more easily extend it. For now I'm just going to load the normal diffuse map, so the normal texture which we are using. But later on with this type we can decide what kind of texture it is, and depending on what kind of texture we can bind it differently, or more precisely send it to the shader differently. Okay, that was the mesh data. It's a pretty simple header file, and let's start the mesh. The mesh will be a little bit more complicated because here where the actual drawing will happen. In the load scene function we just load the meshes and yeah, call the draw function to them. For now there will be just the 3 member function in the mesh file, which is the constructor, the destructor, and the draw function. Later on we can add other things like update the content of the mesh data and stuff like that, but for now these 3 should be sufficient. So let me just include a few stuff which we might need: the IO stream for debugging purposes, and we also include the, let me think, the gl.h, so the OpenGL extension, thing extension, something about the extension. I don't know if we actually need the OpenGL header file in case like this, but if I include it, that's not a problem. Although one thing is for certain, you have to include the GL header file before the OpenGL header files. Okay, include the GL and the GLU header file. Okay, we definitely need the vector, so I'm just going to include the vector. I probably need the string for file names and stuff like that. So string, and the next thing, we will see if we need anything else. So I'm going to make a class called mesh. Actually, we shouldn't call it mesh because we often call variables simple names like that. Let's call this mesh class. Right. Okay, the mesh class will containing 3 vectors about the data. The one vector is the vector vertex data, which we have created right here. So we get the mesh of vertex data. So mesh of vertex data, and I just call this one data. We also need a vector of textures because we have multiple textures. Of course, most of the time we have just 0 and 1 texture, but sometimes later on, mostly in advanced GLSL tutorial, we will have 3 or 4 textures for one simple mesh. So we are going to use a vector of what I call it, texture data. Okay, and I call it textures. So I'm also going to have a vector of indices because we need indices, because the vertex data just containing the vertices. So in case of a cube, it's just containing 8 vertex. And indices, which I'm going to create, will contain which of these vertices actually connected to a face. That's simple enough. So let's just make a vector, and I'm going to use an unsigned integer for the indices. So for example, if there are numbers in this vector like 0, 1, 2, that means that there is a triangle between the 0 vertex, so the data 0, the data 1, and the data 2. Simple enough. Okay, and I just call it indices. Indices. Like that, I believe so. Let me guess. Do we need, of course, we need the vertex buffer object ID. So I'm just going to make an unsigned integer, and I call this VBO. That should be sufficient, VBO. Short and cool. Right. I don't think that, of course, we need one more thing. I just realized we need two buffers. We need the vertex buffer object and we need the index buffer. So I just call it IND, like index buffer. Okay, so public, we need the constructor. The constructor is actually waiting for a pointer to a vector which containing vertex data. So a pointer to this. And I call this vertex data. We need a pointer of texture data which can be null. If there is none, so texture data equals to null, so I give a default argument. And the last thing is we need a vector of indices. Actually, let me put the indices to the second place because indices have to be supplied. So I just call this ID, like index data. Right, I think we are pretty much finished with the constructor. So the destructor will just delete the buffers, so the vertex buffer on direct and the index buffer, so mesh. And the last thing we will need is a simple draw function, void draw. And this is actually waiting for an unsigned integer, which is the ID of the shader which we are using. So unsigned integer program ID. And why do we exactly need this program ID? That's because we are going to give the attributes to the shader in this draw function. So we are going to use a function like so the reason is because we are going to send the data to this shader. For example, we are sending which texture is currently used, and also send the attribute data like the position, the normal, the tangent, and the color, and the UV coordinates to the right places in the shader, because in the shader we are going to have attribute values for all of these. Right, so this is why do we need the program ID, which is the shader which we are currently rendering with. Okay, so that was simply enough. Now let's go to the actual implementation of this. So I'm just going to include the mesh.h. By the way, we should probably add the inclusion guard before I forget. So if and def mesh h, then we define the mesh h and just doing an end if right here. Okay, so we have the inclusion. So let's start with the constructor as most of the time. So mesh, and actually let me just copy this because this is a complex constructor. So copy and paste it right here. And delete the semicolon before I forget. Right, so the next thing to do is so the thing in the constructor, what we are going to do is basically setting the data. So setting the data equals to the VD and the index data to the ED, ID, and the texture data to the TD. So this is the simple part. And then we are going to generate the vertex buffer object and filling up the vertex buffer object, obviously. So the first thing is to let's set the data equals to the VD, actually not the VD, but right like that, the VD. Okay, the indices equals to the ID, and if the TD is not null, then the texture equals to the TD. Perfect. Now we just set up the free data which we have needed. So the next step is to actually create the buffers. So I'm going to call this function GL buffers, which are going to generate one buffer to the VBO variable. The VBO variable is this member variable for the vertex buffer object, and I'm also going to call this to the IND variable. First of all, let me fill up the vertex buffer object. So the next step is to actually bind the buffer. So GL bind buffer, similarly like we do it with textures. And I'm going to bind it to the array buffer. So GL array buffer. So the array buffer, as you may remember from the VBO tutorial, is actually containing the vertex data. So I'm just going to bind the VBO. And the last step is to actually fill up this data. This is a quite simple step. So GL buffer data. So the GL buffer data's first parameter is similar to the bind buffer, which is the GL array buffer. Which buffer do we actually want to fill in? I want to fill in the vertex buffer, which is currently bound. And the next thing is the size in bytes. What is the size which I want to fill up? We can easily calculate this data.size, which is the number of elements in the data, and each of the data is containing vertex data element. So I just get the vertex data size in bytes, so multiplied by size of vertex data. Incredible, we have the size. The next is the starting element of the array. We can easily get this starting element by using data 0. Let me put this into a new line. So data 0, which is the first element of the vector, and there is this nice property of the vector that the vector is storing the data continuously. So like a normal array. So I just get the first element of this and get the address of the first element, and that is at the actual internal array of the vector. Okay, and the last is the flag. How do we want to draw it? I'm just going to go with GL static draw, because we are not really want to change this. Okay, I have the buffer data initialized. The next thing is to actually initialize the index data. The indices can be stored similarly like the normal vertex data, but we have to use the GL element array buffer instead of the GL array buffer to tell OpenGL that this is not something which it should draw. It is something which should be a reference to this other buffer, if it is clear. I think I have said it in the vertex buffer object tutorial, so I'm not going to over-explanate here. Right, so I'm going to bind this buffer as well, so GL bind buffer, and I'm going to bind it to the GL element array buffer. And IND, this is the name of the index buffer, and similarly I'm just going to call the GL buffer data, and actually let me copy this because it's very similar. The first parameter should be changed to GL element array buffer because this is an element array buffer. The second should be changed to the indices.size, which is the number of elements in this indices vector, multiplied by the size of, we are storing unsigned integer, so unsigned int. And finally, this should be changed to indices because we are now getting data from the indices vector, and the static draw can stay right there. We don't want to change the indices that often either. Just to make everything on the safe side, I'm going to bind 0, which is pretty much unbind the buffers, so make sure that no one other people just accidentally change values in this buffer. So GL bind buffer and GL array buffer and just 0, and similarly to the element array buffer. So this is the unbinding basically. Yeah, that was pretty much the constructor. It's not that complicated. If you are not using vertex buffer objects, then you don't need this all stuff right here. You just need to store the data and the indices and the textures in the necessary arrays and use for loops later on in the drawing section. Then the destructor will be almost as simple as that. We just pretty much delete the buffers. So GL delete buffers and delete one buffer which is in the VBO, and let me just copy this and delete the IND. Perfect, we have deleted the buffers, and that was pretty much the destructor, so we don't leave any memory leak behind. The last step is to actually make the drawing. So void mesh draw. The drawing waited for an unsigned integer called program ID, and this will be the most complicated among all of this. Let me delete the default parameter. I don't know why it suddenly came into my mind that I forget, but it did. Yeah, so right here we are in the draw, and the first thing which we should do is that getting the attributes location. In the shader, which we are going to make, or more precisely modify very soon, there will be attribute values in the vertex shader, obviously, called something like attribute vec3, which stands for vector, and vertex, which will be the vertex data. So now the thing is that first we have to get the attribute value of this vertex from the shader, then we activate the vertex attribute array and the vertex attribute pointer and send the data right there. So the first thing to do is making an int vertex and make this vertex equal to the GL get attribute location. The GL get attribute location, if you don't know, it's a similar function to the GL get uniform location. This is giving back not the address but an ID where we find this vertex in the shader, basically. So it gives up most likely 0 right here because this will be our first attribute value. Okay, and right, so it's needing the program ID as the first parameter, and the second parameter is a character literal, which is the name we are searching for. In this case, we are searching for the vertex. Let me just make a few copy of this. And the second is called normal. If you remember, we storing the position, the normal, the tangent, the color, and stuff like that as for each vertex. So the next is we are searching for the normal. This will most likely give 1 to us. The second will 2, 3, 4. So probably if you just write these values down would work as well. So the next thing is the tangent. Okay, and let me copy this into here. The next thing is the color, and copy this to here. And the last thing is the UV, and just copy into here. Did I forget something? Nope. Okay, so now we have the position of all of these stuff. So now we are actually, let's first bind the textures, because we have all of these textures in this texture array if we have it, and we want to bind all of them. So what I thought that we are automatically binding all of these textures. So binding to texture 0, this will be the first texture, then texture 1, and do it until we have textures. So I'm going to make a string with not capitalized S, so string, and I don't know, call it str and texture, just because adding values to textures is easier. You will see in a moment what I mean. So let me just use a for loop to go through all of the textures. So textures, that size I++, and I'm going to just go through all of the textures. So now I'm going to bind the texture to the active texture layer. So GL active texture. This texture waiting for the current texture layer which you want to bind your texture. Defaultly this is GL texture 0. So GL texture 0. Of course this can be GL texture 1, 2, 3, and whatever, for there is a maximum number. I don't know, it depending on the implementation, but usually on modern hardware at least there is 4. So this means that for a single vertex there could be affecting 5 textures. So we can easily, because these are coming continuously, we can easily say that plus I. So if I is 0, then we have the GL texture 0. If I is 1, then we have the GL texture 1, and so on, because these have the values going continuously. So I don't know, if it has the value 100, then the texture 1 has the value of 101. Next is that I'm going to bind this texture. So GL bind texture, and I'm going to bind it to the texture 2D, because most of the time we are going to use 2D textures. I don't think that there will be cube maps or 1D textures in a model file, so we are just going to use 2D textures, and I'm just going to get the textures what was it, ID. Right, we have finished. So the last thing is to actually tell the shader where the number of the current texture layer. So GL uniform 1i, which is sending one integer to the shader, and GL get uniform location. So I'm getting the program ID, the parameter, and I'm sending I to them. Because first of all we bind the first texture to the zeros layer, then the second texture to the first layer, and so on. So it's exactly the same as the I. Alright, we have binded the okay, we have a problem here. The problem is get uniform location waiting for one more variable, right? So we need the str plus the character I. So what it will do is the str is containing the textures, and I'm going to convert the I into almost, wait a moment, so I plus the 0 character. Okay, there we go. So what it does is basically adding, so concatenating the str, which is currently containing texture, with the 0 plus I plus 0, which is first of all 0. So it's first of all getting the location of texture 0. Then it's getting the location of texture 1, 2, 3, and I'm going to create these variables in the shader. Right, there we go. So we binded all of the textures. And now the actual stuff will come, which we are going to draw this. First of all, we have to bind the texture which we have created. So the vertex buffer object and the index buffer. So GL bind texture, and I'm going to bind it to the GL array buffer, and I'm going to bind the VBO. And the second thing which I'm going to bind, not texture, just, we just did the texturing and yeah. So the second thing which I'm going to bind is the GL element array buffer. The element array buffer is binded to the IND. So we have the vertices and the indices bind. So so now we can just tell OpenGL where the data is within these buffer objects. So first of all, we need to enable the necessary vertex attrib array. So GL enable vertex attrib array, and first of all I'm going to enable the vertex attrib array, so I'm going to send the vertices first, so the vertex right here. So I enable the vertex attrib array, and then I'm going to use the GL vertex attrib pointer, which is a function. With it you can tell where are the data basically in the vertex buffer. So first of all, the name, which is vertex. The second argument is the number of components. If you remember, in the vector 3D, we are storing free floating point data. So if I just open up the file, vertex vector 3D, as you can see, we are storing free floating point data. Although this might be a little bit distracting, that actually I'm going to get the address of this vector 3D and get the x, y, z from it, but pretty much the class in C++ is basically the same as just a simple structure with those elements. If it doesn't contain virtual functions. If it contains virtual functions, it's a bit different. But without virtual functions, if I just get the first 4 bytes of this vector 3D, then I get the x components. Although there are a lot of functions right here and methods, but these doesn't really matter doesn't really matter how they are stored in the memory. So they are stored in the memory as x, y, z components and nothing more. So what I'm going to do is basically getting this. So on the basic level, what I'm going to do is just give the address of this vertex data, and the first 3 bytes will be the first 4 free floating point components will be the position, the next 3 floating point components will be the normal, the next will be the tangent, color, and UV. Alright, so I just did a little monologue, but back at the programming, the next data is how many components there are. There are 3 components, the x, y, z coordinates for the vertex. The next is the actual type of these. These will be GL float, so these are floating point number. Just leave the next component to false. We don't really need to care about that component. The next is the striding. So stride, I'm pretty sure this is how it's called. So the data are actually stored one after, so they are actually stored like how it is in the structure: the position, the normal, the tangent, the color, and the UV coordinate. So what we need to tell OpenGL is what is the distance between this position and the next position which it can find. The size is exactly the size of this vertex data, so we can just use the size of vertex data. I hope it's clear. So they are continuously stored, and if it will just continuously read the data, then it will read the position and then the normal, and the normal is obviously not a position. So we have to tell that between this position and the position of the next vertex, what is the difference? So what is the distance in bytes? So we just get the vertex data. Okay, the last parameter is basically the starting point. If you are looking at, again, our structure, it is 0 because there is nothing between here. If there would be a float data between here, then it will be 4 bytes because the floating point data is 4 bytes. But this is just 0 because it starts immediately at the beginning. So just press passing 0. Okay, I'm just going to make a copy because the rest of the data will be as simple to set up as this, or similar rather. Okay, so first of all the vertex, now the normal. So I'm just going to enable the normal. right here as well. And the only difference is actually that it starts in different place. It actually starts after after 3 floating point number, because as you may remember, the position is an x, y, z coordinate. All of them is a floating point number. So it starts after that. So what I'm going to do is just right here, I'm just going to write 3 times the size of a float. 3 times size of the float, although this will result a compile error because this last parameter is actually a void pointer. So I'm just going to cast this to a void pointer. It's a very ugly kind of thing to cast something to a pointer which is not actually a pointer, but we need to do this in order to make everything compile. The next data which we had is the tangent. Again, I'm going to use the same procedure, so change this to tangent, and now we have 6 times the size of a float. So let me just copy this, because there were 3 till here. It has 3, the normal has 3 floating point components, so it's 6. Again, let me go on with the same procedure for the color, and now we have 9. So now we have 9 floating point components. The last one is the UV coordinate. So the UV coordinate is called UV, and actually the UV component is only 2 components long, as you can see, a U and a V component. There is not a third, so I just changed this to 2. And the last parameter is 12, because here it was 9, and it has 3 components, so it's become 12. Right, there we go. We are almost ready. We just need to call the drawing function. The drawing function is, we are going to use the GLDrawElements function. There are other functions which can actually draw from vertex buffer object, but the GLDrawElements is just using the indices, and it's going to draw it. So GLDrawElements. So the GLDrawElements, first of all, waiting for the kind of shape which we are going to draw. We are going to only draw triangles. We are not care about the quads or any other kind of object. We are only drawing triangles. We are going to make sure in the loader that we only get triangles by triangulating everything which is not a triangle. So I'm just going to use a GL triangle right here as the first parameter. The next is the number of indices. Basically not the number of indices, but how many triangles we want. So the second is the number of indices, right? So we can easily get this with the indices at size. The next parameter is the type of the indices. As you may remember, I use unsigned integers. So what I'm going to write right here is the GL unsigned int, which is a building constant for the unsigned integer type. The last is just 0. Usually you could pass it an array of indices right here into this pointer, but because we have already binded to the index array, we have to pass 0. So yeah, we only have to pass 0, and there we go. So what I'm going to do now is just disable everything which was enabled and unbind the buffers. So GL disable vertex attrib array. Too many R. And I'm just going to disable the vertex. And let me just copy and paste this. I'm going to disable the normal, going to disable the tangent, going to disable the color, going to disable the UV, and then I bind 0. Actually, let me just copy that. I bind 0 to the array buffer and the element array buffer. And there we go. So no one accidentally do something which they didn't intend to do. And we are finished with the mesh class. Now we have reached the actual part of the tutorial, which tutorial is about, loading the actual object. So this mesh is just storing the object, but the scene loader which will actually loading from the file. More precisely using the Assimp to load it from the files and use the data from the Assimp to load what we only need. Right. So first of all, let's start with the inclusion guard, so we don't run into problems from this. And scene loader underscore h. Okay, so the class is called scene loader, and the scene loader class will be relatively simple. It will contain only only an array of meshes, so std vector mesh pointer, and I just call it meshes. So this is using this mesh class which we have created just a moment ago to store all of the meshes, because one scene can have multiple meshes. Mesh.h. And also probably we need some more includes, actually a lot of includes like the vector. And I'm also going to include the Assimp header file. The Assimp header file, there are a lot of header files. If you just open up the folder, as you can see, there are a lot of header files which you can include. Probably most of them are included somewhere, so we don't have to include all of them. I'm going to include 3 which is included in the code. So there is, by the way, code here, not this test, but sample code right here, and GLUT, and right here there is a GL, not this. There was somewhere a sample code. Simple OpenGL, yeah, that is it. So right here, this is the C code, if you want to check this out. I'm going to include just this 3 right here. Actually, no, because this is the C importer, I'm going to use the C++ importer, but I'm going to include these 2 because, as you can see, these are usually included. So, I'm going to include the importer.h. The importer.h is the C++ importer. It's using object instead of function, so this is why it's a C++ importer and has constructor and stuff like that. We don't really have to care about this. For now, later on I will show you how to use it. The second which I'm going to include is the assimp/scene.h, because we are going to have an AI scene which is in this header file. And the last one which I'm going to include is the postprocess.h. So assimp/postprocess.h. This header file, actually this is not capitalized, containing a few useful constants which we are going to use. Let's see, what else do I need? I don't think that I actually do need anything else for this file, but we will see. Okay, so I have a few private methods as well, which later will make sense. What are they? So one is the recursive process. This is a recursive function which will process the entire scene, because some type of files like the .blend file actually containing hierarchical stuff, so like a tree, you know how the binary tree look like, so something like that. Every node have children and have a father, father, I believe these are called father. So yeah, this is it. I don't want to talk about more on this, you will see in a moment. This will wait an AI node. We will explore these structures in a moment. And second which wait is the AI scene. Okay, it's an important thing that make it constant, because the importer will return a constant AI scene, and if you don't make this constant right here, it will not compile. Then I also have a process mesh with process mesh. This process mesh will actually get the actual data from the mesh, and this have an AI mesh as a first parameter mesh, and the second parameter is a const AI scene, just like in the first case. Okay, the third private method is the load texture function. I'm just going to copy it from the OpenGL tutorial 22, I believe so. So it returns an unsigned integer, call it load texture, and it's waiting for a const char pointer file name. Alright, the public function will be, of course, the constructor and the destructor. So mesh loader, the mesh loader will actually waiting for the file name, so const char file name. The destructor, mesh loader, and I will have a draw method, draw. The draw method will wait for the program ID. It's waiting for the program ID because we have to call the draw function of the mesh for every single mesh, at least for now. Of course, we could have get each meshes separately and call each mesh with a separate shader, because not all meshes have to be drawn with the same shader. But for the simplicity, this draw method just goes through with the for loop all of the meshes and call all of the meshes. Later on we can use a getter function to actually get a simple mesh and draw that mesh. And actually let's make a getter function for that. So it's return a mesh pointer and get mesh, and I don't know, just use an ID or something to get a mesh, and then we can draw that mesh separately if we want to. Or even better, if just return the meshes array. So mesh pointer, and then we don't need this, get meshes. Right, pointer right here. And we should return with the reference to it. Alright, so I think it should be good. Okay, so after we make all of these functions, we only need to modify a little bit the main.cpp, and we only need to modify the vertex and the fragment shader a little bit, and we are ready to roll. So let me just copy this and paste it right here. We are going to include the scene loader. So include scene loader.h, and let's start. We don't need this. Let's start with the constructor, because I want to go in the order how the data will be actually going. So the mesh loader constructor will first of all create an importer. Alright, so right here the importer, and one thing I think I forgot is the HPP extension. The importer don't have the .h extension but have the HPP extension. Sometimes this HPP extension is used instead of the normal H extension to make sure that the user know that this is a C++ header file, not just a normal header file. It doesn't actually really matter, it's just same as normal header files. Alright, so I usually like to open up the header files to check what are they containing. So this is containing a namespace called Assimp, and right here it's containing an importer. This is what I'm going to use. So we need to create a instance of this importer, and this importer is actually somewhere right here, importer. And the important function in this importer is the read file. So it should be somewhere here. If I do a search for it, read file. Okay, the read file function right here, it's waiting for two parameters. First is the file name, obviously, and then the flags. These flags are actually located in the postprocess.h. So let me just do a quick search for it right here. So postprocess.h. And these are very useful flags, like calculate the tangent space. For example, we are going to use this. Then we are going to use the triangulate to make sure every shape is a triangle, so there are no quads or other type of shape. Right, and we have a function generate normal. The generate normal will generate normal if the normal is not in the file, or generate smooth normals is even better, which is generating smooth normals. So right here, let's start with making this. I should do something with anyway. So we need to create an Assimp : importer. Assimp : because it is in the Assimp namespace, as you have seen, and importer because we are going to create an importer, and I just call it importer to make everything simple. And it will return a constant AI scene pointer. I just call this scene. And so we are going to use the importer.read file with capital R and F. So the first parameter, if you remember, is the file name. So I'll just write file name into here. The second parameter is the flag. So let me just close all of this up so we can just easily click here to the post process. And you can use just the binary OR operation to concatenate these flags. So I want to generate smooth normals. I want to triangulate. If I find it, I process the triangulate. I'm not going to type all of this. So using the binary OR operation to concatenate these flags together. I'm going to also use this calculate tangent space. So we have tangents, because although these tangents are not useful for this tutorial, in the normal mapping these are very important, so we don't have to manually calculate them. Okay, let's see what else is useful right here. Another useful is the flip normals. If I just find it, flip normals. I just do it a quick search because as you may remember, similarly like the OBJ file loader, the UV texture Y coordinate is on the opposite way in the OpenGL like it in Blender program or something. So it's pretty useful to have to flip the normals. Yeah, that's pretty much it. So we have imported the scene, and now in the constructor we don't have to do pretty much anything else. Just just call the function of this recursive process, which will going to process this scene. Before I do that, I do an error check though, because there could be errors. For example, if the file is not existing or there is a problem with the file, so we don't want to process if there is a problem. Now the flag, there is a scene and m flags. This is a member variable. Let me open up the scene.h2, not here, scene.h, and it's containing the AI scene, not the AI node, but the AI scene right here, AI scene. So here is the flag. By the way, you can see that this is a very well commented header files, all which I have encountered in this library, so I highly recommend to check them out if you don't know something. So the M flags containing all of the flags, and there is and this is defaultly 0. So I'm going to just check if it is not 0. So I'm just going to use the binary negate operator. So actually not the binary negate, the logic negation operator. So the not operator right here to check if it is not 0. Then I'm just going to write out some error message and exit from here. The file wasn't successfully opened. And I'm also going to write the file name right here, so if we have multiple files, we know which file was not opened correctly. Perfect, and I just return from here. We don't need to do anything else. Okay, now I just call the recursive process, which will start from the scene. Again, let me just open up the root node. The root node is the root of the tree, obviously. So yeah, I'm going to call it with the root node if the root node exists. So if root node, actually let me write it here, or not root or not scene root node. So if the root node is null for some reason, then we have a problem too. Now actually this is m root node, isn't it? So m root node. So I'm just going to call this recursive process. We don't need this check. So recursive process, and the recursive process first parameter is the root node. So I just get the scene root node, which is an AI node. If you just check it, as you can see, an AI node pointer, just as the recursive process weight. And the second parameter is actually the scene itself, because we will need this scene later on. I will show you in a moment why do we exactly need this scene as we write this recursive process. The recursive process will recursively process everything in the hierarchy by first process the current node, the current mesh, and then call itself to all the other children node of this node. So this is why it is recursive. So let me again just go to the scene and let me go up to the AI node. Right here, the AI node. The AI node is containing a name. We are not using this name for now. We have this transformation. Later on, I will add support to actually store and send transformation to the shader, but for now, we don't worry about the transformation matrix. The parent, we are not worried about the parent either. What we are worried about is the number of children. So right here, I'm just here we do the processing. So let me just write here process, and right in the end here we do the recursion. So I'm just going to use a for loop for int I equals 0, I less than the number of children. So node m num children I++. So I just go through all of the children, and then I call the recursive process. So I will call this function itself with the node m children. The m children is right here, an array of children, basically an array of nodes. So children I, and the second is just passing the scene right there. Perfect. So what it's going to do is making the recursion the stopping of the recursion is if there is no children. We are going to make simple scenes, so we don't have to worry about getting into a Stack Overflow or something. So it most will load once or twice. For OBJ file, it doesn't even support here or here, so for that it will not even load. So it will not even run even once. Okay, then the process, right? So the process is going through all of the meshes, because a node can contain multiple meshes, as you can see, num meshes, and all of them are stored in the AI scene. So AI scene. So the AI scene M meshes array containing all of the meshes, while the AI node is just containing a pointer. Right here, the pointer to each of the mesh. So right here, I'm going to make another for loop for int I equals 0, I less than the node M num meshes. So all of the mesh I++. So I'm going through all of the mesh. I'm going to create a AI mesh pointer mesh, and this will be equal to I get the meshes from the scene. So scene M meshes, and I get mesh is like that. Okay, and then I'm going to get the current mesh, which is the node M meshes I again. So what I did is basically, first of all, I get the ith element of this array, which is just simply an index, and then I go to the scene and I get the ith mesh from this array, a pointer to it at least. Okay, and now I'm just going to call the process mesh function, which is waiting for, as you can see, the mesh itself, which we have just got, and the scene. The process mesh function will be the one which is actually doing the hard job. So let me just use this mesh loader : to everywhere, because I forget. Usually I make them. So this process mesh will be the one which actually gets the data and putting it into a vector and creating the mesh, populating the mesh array itself. So to do that, now we have reached the end. Getting data from the mesh is relatively easy. I have opened up the header file as usually, and we will see as we go along. We just pretty much have to copy from this structure the data to our vector, and there we go. So the AI phase, we will need that in a moment, but first of all we need the AI mesh, not this, but the AI mesh. So we have a primitive type. We don't really have to care about this, but this is currently set to triangles, because as you may remember, we have triangulated the mesh right here, triangulated. So we pretty much sure that this is triangles. The number of vertices, this is something which we will care about, so let me just make a for loop right here. Int I equals 0, I less than m num vertices. M num vertices I++. So I just go through all of the vertices, and actually before I do that, let me create a TMP mesh. So we call this vertex data. You remember this is the structure which our vector contain in our mesh class. So right here, not this mesh, but our mesh class. So right here, the vertex data. So I'm going to create a vector of vertex data. So a vector of vertex data, I will just call it data. I will create also a vector of indices. So unsigned integer indices. And I'm also going to create a vector of textures. So texture data, textures. Okay, so I create three data. This is, as you may remember, the exact same stuff as we need to create a mesh object. So I'm going to create a vertex data right here, a temporary vertex data, TMP. At the end of this loop, this vertex data structure will be filled in with the position, the normal vectors, the colors, and so on. I'm also going to create a vector 3D TMP vec just to make our life easier. So first of all, let's see the position. The position is stored in this M vertices AI vector 3D structure, and yeah, M vertices. So I'm just going to get the X, Y, Z components from the M vertices and set it equal to our TMP vectors X, Y, Z. So TMP vector dot X is equal to the mesh. I get the M vertices from this, and I get the ice vertex X component. We cannot directly do the equal sign, so make the TMP vector equals to the M vertices, because there is no such operator. Of course, we could write such operator, but I'm just going to write it in this way. It's not that complicated. And right here, I'm just going to set the TMP.position equal to our TMP vector. There is equal sign right here because the position and the TMP vec is a vector 3D. So we set the position. Let me write here position. The next step is to read the normals. To read the normals, we are going to use the M normals array, and pretty much I'm doing the same thing. So let me just copy this stuff right here, and just write normals so we know what are we doing right here, and I get the M normals. Normals. By the way, this M stands for member variable. This is often used in libraries. Okay, the next step is to get the tangent, M tangent. We although generate tangents, we are making let's make sure that we actually have tangents, because if we don't have tangents, then we would access to a null pointer, and that would not be good. So I get the mesh M tangent. Okay, so if it is not null, then I'm just going to do the same thing right here, except I'm going to use the M tangents I. By the way, both the vertices, normals, and tangents are in this for loop because every vertex has a normal and tangent. Okay, as I just do something, I don't know, making TMP vec dot X equals TMP vec dot Y equals TMP vec dot Z equals 0. Or maybe make the X equals 1 and the rest of them are 0. Okay, and I'm just going to put the... Oh, I forget to change. Good thing I noticed. So normal, and right here this is tangent. The next step is the color. The color is in the, not the bitangent, but here in the M colors structure. This is an AI color 40, so 4-dimensional color, and it has maximum number of color sets, so it's an array. So first of all, we have to check if there are colors. So if mesh, and I get the M colors 0. There could be several colors associated to a simple vertex. We only care about the first color. We don't really care about the rest of the colors for now. And most of the time, the first color not even set. So this color is really not all that important. Okay, so if there is a color, then I'm just going to do similar things like I did right here. By the way, let's add a comment. Tangent. Tangent. Okay, tangent. And right here, let's add the colors. Okay, so if there is a color, then I'm going to set that color. Else, if there is no such color, before I forget, let's change this to color 0i. So I get the 0th color, and for this vertex, basically. As I'm just going to set tmp vec.x equals the tmp vec.y equals the tmp vec.z. By the way, I think we made a change member function. Okay, and I'm going to just make it to 0.7, so it's a kind of grayish color. And let's set the tmp dot color equals to this tmp vec. Perfect. Now the next thing to do is on the list what as the UV coordinates. Right, we need the UV coordinates, which is right here conveniently, and we get it basically the same way as we did in here. So add a comment, color. Okay, so we use the M texture coords member variable right here and here, here and here, and just set it 0 if there is no such thing. Okay, and this is set the U equals to the, actually there is no Z coordinate. So set the U equals to the tmp vec.x and set the V equals to the tmp coordinate.y. The V. Okay, I think we did all of that we had to. So in the end of this stuff, this TMP, so this vertex should be filled up. So we don't need to do anything else, just push it back to the data. So push back TMP. Okay, so this data and the end of the loop will contain all of the vertex data. Right, the next stuff we have to do is actually getting the indices. To get the indices, I'm pretty much just have to go through this m faces array. So let me again make a loop. For int I equals 0, I less than m num faces. This is the number of faces, I plus plus. By the way, if you do this, these are pretty self-explanatory names. So num faces and num vertices, so pretty much tell you what they are. Okay, so I get a face. The face is just an AI face. So let me just make an AI face right here. I just call this face. This is not a pointer, and this is just the. And actually, I forget here. I should put node mesh. I get the faces from the mesh. So right here, this is equal to the mesh and m faces I. So I just get the i's face, which is, as you can see, a face. Now we find the face up here in the top of this file. Right here, AI face. It's a pretty simple structure. It has the number of indexes, pretty much how many vertex build up this face. This will be free in our case because we triangulated the mesh. And we have the m indices, which is the actual array for the indices. It's used unsigned integers, similarly like our array. So we have a pretty simple thing to do. Just use another for loop in j equals 0, j less than the face dot m num indices, j plus plus. So, by the way, this is the same as if we would go to free because we triangulated the mesh. So this is free, 0 through 2, including 0 and 2. Okay. So we have we go through the faces and we get the j's face from this. So indices, which is our vector, we just define this vector up here, indices dot pushbacks. So indices dot pushback. So I'm just going to get the face dot m indices j. I think I did it as it should be. Let me just m indices and I get the m indices. I think I did it as it should be. We are almost finished. One last step is to handle the textures. So the textures are stored in a structure called AI material. It's another structure, and let me open up the header file for this. This is pretty much just storing the texture. Although it says material, it doesn't actually store anything else. It stores different kind of textures. Okay, to get what texture, what material the current mesh is using, we are going to use this unsigned integer. This is an index, so m material index. And we are going to go to the scene, and we have m materials right here, m materials, and index, which I just show you in the mesh right here, this m material index is an index for this material. So what I'm going to do is to get the material, I'm going to get the scene m materials, which is that array which I showed you, and then get the index of get the m material index material from this array. So mesh and get material. Actually not get m material index, sorry. So m material index, I just get this material. I have a material. Now I'm going to the one material could contain multiple textures actually. So to get how many textures do we have, we are going to use a function called get texture count. Let me just search for it. Get texture count right here, get texture count. It's waiting for the texture type because there could be different type of textures. For now in this loader I'm going to care about the diffuse textures only. If you want you can go on and load in the normal maps and load in the different kind of, there are a lot of kind of different texture which you can find. And if I just do a search for it, how many. Right here, the diffuse map, specular map, ambient map, emissive map, normal map, height map, shininess, opacity. So you can see there are a lot of. I'm only going to care about this AI texture type, diffuse. So only the diffuse. Okay, so for int I equals 0, I less than, I get from the material, I call the get texture count member function, and I get the diffuse texture. Okay, I++. So it tells how many texture does it have. Most likely this number is something like 1 or 0, but it could have up to 4 or even more. So whatever many texture that can be for one simple mesh. Okay, the next thing is that we actually want to get the name of this texture, so where it is. So I'm going to create an AI string str, because we need an AI string, because the function called get texture return with an AI string. Let me just show that too. So get texture right here. It has a lot of parameters, but as you can see, most of them are default parameters, so we don't really have to care about them. You can read them if you want to, but I will not for this demonstration. So first of all, the type. The type is this AI texture type diffuse. So I just get the texture, the diffuse texture. The second parameter of this function is the index. I want to get the i's index, the I, which is my loop variable, and then a pointer to an AI string, and it will put the path into there. So I just use the address of str, and it will put the location where this image file is located. Alright, the next step is to actually load this texture. So I'm going to create a texture data tmp and make the tmp.id, which is the ID of the texture, equal to the load texture, and I get the string data from this AI string, which is get by c_str, similarly than normal C++ string, except this C and S is capital. Okay, so this will be just pretty much loading the texture and return with the loaded textures handle ID into this tmp.id. For now, I just set the tmp.type. I believe this is what I call to 0. Because this is a diffuse map. If we are going to load other kind of maps, this type will be different, but for now this demonstration doesn't require to do that. Okay, and the final thing to do is just push it back to the textures. So textures that push back, and I push back the TMP. Alright, now we are finished, so we can push the mesh back too. So mesh.push back, and I'm just going to push back a new mesh. And the new mesh will contain the data, contain the indices, and contain the textures. Actually, the address of these, I just realized. So just get the address of the data, the address of the indices, and the address of the textures. There we go. We are finished with the loading function. This was all, although this works only for static meshes for now. The part 2 of this tutorial will show you how to load in skeletal animation. But for now, the static mesh will do, because this tutorial will be extremely long. And what else did we not finish? The destructor. The destructor will delete all of the meshes. So let me just use a for loop int I equals 0, I less than meshes. The size I++, and I just use the delete to delete the meshes I. That was simple enough. Okay, the draw function will be almost as simple as that. I'm just going to use the for loop. Same for loop as here, but I'm going to call the draw function of each of those meshes. So meshes I, and I just call the draw function with the program ID. Okay, if you remember this, this draw function will set up all of the vertex buffer properties and just draw the mesh. The get meshes will just return the meshes. Return meshes. And did I miss anything? Of course, the load texture function. Let me just go offline and copy it from my earlier tutorial. Yeah, and here we are. I just copied it from directly my tutorial. This is the same code as I did in somewhere like 22 OpenGL 22 tutorial. So this is the program which are capable of opening textures. And I realized we need to include the SDL image if we want to be able to do that. So let me just find the header file, sceneloader.h, and let me include right here the SDL image, include SDL/SDL_image.h. Perfect. I believe we are ready with the scene loader, so let me go into the OpenGL.cpp and let me include this scene loader. So include scene loader.h. Okay, and let me immediately create a scene right here. Scene loader, and I just call it scene. And actually, let me make it a pointer and use dynamic memory allocation. Okay, so somewhere in the init, I'm going to initialize this. So make a scene equals to a new scene loader, and what file should we try to load first? Let's try a normal OBJ file, and then we test out how it's loading the blend files and other type of files. For now, just the simplest test which is possibly out there. Okay, before I forget, we should just delete the scene. Alright, we have the scene. So I'm going to just call the draw function instead of this triangle. So scene, and I'm just going to call the draw function with the program ID. The program ID is in the variable program from earlier, because as you can see, we use the program right here, GLUse program, and we don't use the GLUse program 0 or other GLUse program, so we are using still the program. This is the ID, and almost there. We only need to modify the fragment shader and the vertex shader slightly bit. Alright, so here are the vertex and the fragment shader which we are going to use. So let me create those attribute variables. So attribute and vec3, and we call the first attribute variable called it vertex, I believe so. Then let me make an attribute vec3, and the next attribute variable was called normal. Again, make attribute vec3, and the next one was called tangent. Make another attribute variable vec3, this one called color, and make another attribute variable, this is a vec2 not a vec3, and call this uv. Okay, we changed this line slightly bit by not using the built-in GL vertex, but using the vertex instead. As we are going to change the built-in matrix, we are going to change this parameter right here and then this parameter as well. So no built-in variables will be used here. Okay, and let me make a few varying variables. The varying variable, if you remember, give data from the vertex shader to the fragment shader. So varying vec3, and this one will be called out normal. And let me make a few of these. Out normal, then we have an out tangent, then we have an out color, and we have an out UV. Alright, so let me just fill up these variables. So the out normal equals to the GL normal matrix times the normal. The out tangent is equal to the normal matrix times the tangent. The out color is just simply equal to the color, but these will be interpolated. And the out UV is equal to the UV just interpolated. Okay, we have the vertex shader ready. Now in the fragment shader we need obviously the varying variables. We also need a uniform variable, uniform sampler 2D for the texture, and I call this texture 0. Of course, if there are multiple textures, then texture 1, texture 2, but for now the texture 0 should be sufficient. Okay, the color should be, let me just make the color for now equals to the out color. And there we go, we are finished. So now the debugging section will come. First I export out that OBJ file, so I'm just going to add a monkey object. So just write monkey, add monkey. This monkey will be good, and I should probably add some properties to this monkey. Let me find where are the material properties can be added, and let me just, I don't know, try to change the material property. Okay, so I just changed the material property right here, and I am ready to export out as an OBJ file to my desktop, and I call this OpenGL Assimp right here. Okay, and I call the file test.obj. So I have exported it out, and I hope it is in the folder as well. Yes, the obj and the material file named test are here, so we can now try to compile it and see how many errors did I make. I don't know, probably a lot. So I'm just going to go into my folder slash desktop slash OpenGL Assimp. Okay, and there should be a compile command somewhere. By the way, to compile, that's a lot. By the way, to compile a program, that's very a lot. To compile a program with Assimp, use the Assimp compile flag. Okay, so first of all, the vertex data was not declared, so probably it is not included in the mesh.h file. So let me just search for the mesh.h file, not this. Indeed, it's not included into here, so let me just include the file called mesh data into this mesh. So include mesh data.h. Okay, that should fix a few of those errors. I hope a lot. There are still a lot of errors. A little bit less. Okay, the problem is that mesh has no type in the mesh.h line 18. Because it's called mesh class. Of course I call it mesh class and I use mesh everywhere. Okay, guess I have to just rename these and rename everything in the CPP. Wanted to call it mesh at the first. Okay, and change this in the, you know what, let's just do everything back and call this mesh class mesh. So let's call this mesh class mesh instead. It, I think, will actually have probably few of the variables, because some of the variables are actually called mesh, but we will deal with them later. So let me try that again. Okay. First, it's time to fix some errors. I actually went a little bit off screen and write down most of the errors which we need to fix. Although in the terminal we have a lot of error, but basically these are all which causing it. So first of all, let's go to mesh.cpp, and so basically this should be the first error. There is too many closing parentheses in line 47. So we just delete the closing parentheses here and get the C style string from this C++ string object, because the get uniform location is waiting for the const char pointer instead of a std string. Okay, so this should fix a few errors. Again, mesh.cpp, I have GL triangle which was not declared, so let's just let's just rewrite it GL triangles, which is the right name for it. Okay, this was a very stupid mistake from my part. First of all, I wanted to call this class mesh loader, and then I called it scene loader, and then somewhere I wrote scene loader, somewhere I wrote mesh loader. So we can quickly fix that right here. So we can quickly fix that by calling this mesh loader. As you can see, this is how I called the constructor, and basically this is how I called everything. Yeah. Okay, that should fix another few errors. Okay, the scene loader. Here I use the m num vertices, but actually it is in the mesh, so this member variable, not just the global variable. Let's see something other. Scene loader and line 60. So line 60. Right here, the M colors, although I store the color similarly in a vector which has XYZ component, the Assimp actually store it in a separate structure called the M color, color 4, because it's storing the alpha component, and it has RGB value. By the way, this is not the same, not equal to the material color. It is actually a separate vertex color which you can get by vertex painting in Blender. Usually we don't really use that. And by the way, just if we are here, let's just change this to 1.0. So if some shader want to mix the material color and the texture color, then it just gets one, so it's getting the vertex texture color, right? All right, and scene loader and line 100. So let's go again to scene loader, line 100. The problem is that I have this variable, member variable mesh, and also I have the same class name right here, mesh. So what I can do is getting the constructor to run, because if I just write mesh here, it thinks I want to create a new integer, so it's like writing a variable name here. So I just write mesh : mesh, and it should solve some issues. The best solution would be to actually not call this mesh, but call this mesh class as it was earlier, but then we have to change a lot of stuff all over the place. So I just simply call this, and maybe off screen I rename it. What else? Okay, we had a few issues in both in the fragment and in the vertex shader. I didn't define what are those, but I think I can find this out. So the vertex is a vector 3, and the model view matrix is a 4x4 matrix. You can multiply a 4x4 matrix by a 3-component vector. It has to be a 4-component vector. So I just simply going to cast this with the constructor to a 4 element vector by writing the W component 1.0, which exactly what it should be, because that's how we get the right perspective projection. So usually you always want to set the last parameter, the W parameter, to 1. The model view projection matrix, when you multiply, will set it to something else, but it will automatically do something called perspective division. So it should be always 1 to make the right perspective projection, and it will automatically do something after the multiplication, because this 1 will not necessarily will be 1 after this multiplication. It will automatically divide with this W component, and that's actually what makes further object look smaller, basically. So we really don't really have to care about this, just set it to 1 and the perspective division is done automatically. What other? Okay, so the normal matrix is actually, there is an underscore here, GL underscore normal matrix. Let's see how I don't see any other problem right here. So let's just go to the fragment shader and let's see what did I screw up here. Of course, the GL frag color, which is the output, is a 4-component vector. So let's just make this a 4-component vector and add the alpha component 1.0. It doesn't really matter what the alpha component is, because I'm not using blending, so the GL blending is not enabled. Right, let's try to compile it again and see how many errors did I miss. So if I just compile it again, yeah, I had a few in mesh.cpp47, so let's take a look what should be there. So mesh.cpp line 47, again an error here, and let's see the problem. I have again a problem with the parentheses, so I move this one back. Right, this should be how the parentheses are, because I did another parenthesis right here to cast this. Okay, let's add another parenthesis just to be on the safe side, and that should be closed here. Okay, I believe this should work. I think so. Okay, so line 47, oops, that's another. So error in line 47 has fixed. OpenGL.cpp line 15. I know what's the problem there. This is not called scene loader anymore. This is called mesh loader, because I screwed up the name. Okay, let's try this again. Line 87. I create a new mesh loader. Perfect. I think we got them all. So now let's try to run this and see what errors does the shader give us. Okay, incompatible types on the vertex shader line 18. So let's see line 18. Of course, this is a vector 2, not a vector 3. The UV coordinate was a vector 3 right there as well. Let's try this again, and we get a black screen. Apparently, this test is not good as it should. It is not as it should be, but we should check if it is equal to AI scene flags incomplete. Because if it is equal to this constant, then we have a problem. If it is null, then apparently it's okay, because for some reason it entered here. As you can see, it's right, the file wasn't successfully opened. So now, if I have a little luck, it will run without errors. And yeah, it did. As you can see here as our Mankey object, although it doesn't have colors, that's because, as I said, this is this color which is in somewhere here where we read out the colors right here. It is not equal to the material color which we have set. To get the material color, I will actually go here to the beginning of this processing mesh right here before I actually getting the vertices, and now I am getting out this from the material. So AI material and MAT, and I get the material similarly like I did down here. Actually, I will copy it because that will be a bit quicker. And then I can use a function. So let's change that and actually add the material color. And if there is no vertex color, then set the material color instead of 1.0. We can do that right here. But first of all, let me move this material up right there, because we need the material, because the material containing the color. Okay, so we are going to use a function called get material color, and actually AI get material color. So AI get material color. The first parameter of this function is the material itself, so MAT, which I have declared up here. The second is the property I want to get, GL. So let me see. So the second property is what material do I want to get, AI underscore mat key underscore color underscore diffuse. This is the diffuse color, and I want to put it into a AI color for the object. I call it COL. Okay, so I'm just going to put it into the COL. So I get the address, and in theory now the COL should contain the color. So let me create a vector 3D and call it default color, and let me just fill this up with the col.r, col.g, col.b. Right, and make the color equal. So the TMP vec equal to this default color if there is no material color. So let's see what is going to result. And as you can see, we get our red Mankey head as I have exported it out from Blender. As you can see, it was red. So let me just try to change this quickly and see if it is indeed does the right work. So I'm going to still export out as OBJ file, but we will test out some other formats in a moment. So test.obj, exporting, and more exporting. Perfect. So let's see. And indeed, it's purple. So let's test a few formats. I actually did a little bit of testing, and I found out that the newest Blender version .blend file cannot be imported for some reason. Probably it will be soon fixed. But till then, I have the older version. So this is the 2.49 version, and this is worked. So let's just save it. Save. And I'm going to not save it here, but save it to the current folder where we are working, and I just call it test.blend. Okay, it is saved. So let me just go into the code and load it. So in the OpenGL.cpp, I just change it to blend. So try to load the Blender file. In theory, it should work. So as you can see, I'm compiling and running, and indeed it's loaded in. It's not rotated 90 degrees. like in case of exporting the OBJ file. But it does loaded it. So let's try a few other formats. Let's try what else are in here. Let's try 3D Studio. Okay, test.3ds, it will be a good name, just as any. So 3ds. Okay, that format loaded as well. So let's see what. Oh, Collada. Okay, should go into my folder. So home here, desktop, and open up. That's right. So what should we call it? This should be test dot. What is the extension of Collada? DAE, I believe so. Okay, exported, and do I need to press anything else right here? Export and close. I think it is exported, but let's see. So DAE. Alright, and let's try this format as well. It is loaded. So as you can see, you can load a lot of format. The part 2 of this tutorial will show you how to do animation, but for now it was a long tutorial already, so thank you for watching and